Testing. Okay, it looks like we're working. Oh wait, one of the logical things that we're going to want to talk about when it comes to impulse, something that changes your mass or velocity, right? That oomph that gets it going, right? That force over a period of time, right? Is a collision. Things are going to ram into each other and collide. I like using sports. I think sports is a great analogy for that. That's why I have at least 2 photos on here, right? I already talked about the idea of if you put a baseball coming in at one speed and coming out at another speed, like it requires a tremendous amount of force to change that impulse to change that direction of the baseball by that much, right? So even the tennis racket, right? This is a good example of how much compression the tennis ball is going to have, or even just a collision between these 2 rams here. Okay, so we're going to talk today about how to do some calculations based on anything that collides with each other. And I think this line right here really narrows down like the possibilities. Either you're going to stop an object, you're going to slow it down, you're going to send it in another direction. There is a 4th possibility I never wrote down. You could also speed it up. Speed up. I think those are really the 4 possibilities, right? An impulse could stop something, deaden its tracks. It could slow it down, like brakes. Brakes are an impulse. When you are using brakes in your car, you are applying a force over a period of time. If you use your brakes longer, you'll slow down more, right? Okay. It could get bashed back the other way, like the baseball or the tennis ball, or you can even speed it up again. That's an impulse, right? Anything that changes its inertia is an impulse. Before I go on, I need to make sure you guys know some terminology that you'd have picked up in previous classes. Have you guys heard about the 3 types of systems? If I talk about open, closed, and isolated systems, is that familiar? I'm getting a lot of nods. I mean, just in case it's not, let me give you the quick review. An open system is the kind of system where both stuff and energy can freely flow. For example, when the door is open, you guys can physically go through it. You are matter. And energy can come in and out of the room because there's vents that let hot and cold air in. So this is an open system when the door is open. Close the door, and now you can't get out of the room. Now it's a closed system. But can energy still come in and out? Sure. Energy almost always transfers of some kind. Isolated systems are like highly impossible because not only does matter have to get blocked from transferring, but energy would as well. And I mean, the best thing we can do for an isolated system would be like a thermos. And even then, is a thermos going to eventually like cool down? Yeah, it'll take a while, but eventually energy will be like lost, quote unquote. But we like to ideally consider that we're working in an isolated system, where what I'm trying to say is that we're not going to change our mass, and ideally energy should be consistent as well. That's what we're hoping for. What I mean by this is then, I gave you this example the other day. Imagine that you break something. I want to assume that the mass that you started with is going to be the mass that you have afterwards. It's not going to like shatter into a million pieces and you're like missing a little bit. Or there's not going to be like a bird that somehow flies into our scenario and lands on our car and makes the car heavier, right? So both mass and energy have to be consistent. If that is the case, there is a law of conservation of momentum, which basically says however much momentum you have before a collision occurs should be the same amount of momentum that you have afterwards. I don't know why I wrote it in that order, but you guys know how there's laws of conservation of mass, laws of conservation of energy. There's a law of conservation of momentum. Okay. So, and I'm going to use that to try to describe this picture right here. This cannon right here. Does anybody know why there is a rope on the back of it? Exactly. Stops the recoil, right? Because you shoot the cannonball out this way, we have now sent a mass and a velocity out that way. Well, if momentum is to be conserved, should there not be a mass and a velocity going back the other way? It's no different than the recoil in a gun, right? You guys have already learned this concept because it's Newton's third law. Right? Only now we're accounting for time as well. So here's what I need to be able to teach you guys. There are 5 types of collisions that you're expected to be able to do. Okay. The first 2 are linear. You guys know the word linear? Like straight line, 2-dimensional. Or actually 1-dimensional, like just like a linear. Here, let me just do them one slide at a time. I got pictures here, okay? Here's a linear collision. The cue ball runs into this ball right here. This one comes up here, it hits this one, and it keeps going forward. That'd be a nice linear collision, and the objects have separated. Right? I'm not worried about it going in this direction or this direction, so like I'm ignoring side to side. We're just going in a straight line. Okay, those ones are pretty easy. You could also have a linear collision where they stick together. Like, for example, someone gets rear-ended, and all of a sudden one car and the second car are kind of like crunched, and they're now like one big super crunched car, right? And so like they're now combining their masses. Third possibility is an explosion. We'll do that with the methanol cannon with the duct tape another day, whereas one thing goes this way, another one goes the other way. Third one, or the fourth one, now we're talking two dimensions, like getting T-boned. This would be where someone's coming from this way, someone's coming from this way, and they crash into each other on the side. This now needs to take into account two dimensions. You guys know how to do like the X and Y components of things? I'm hoping at some point last year or whenever you took physics, maybe you know how to do like the velocity in the X direction, velocity in the Y direction. We're going to have to break these up into vector sums. I'll show you how if you don't remember. And then the final one is like a glancing collision. This would be like where there's a curling stone just sitting there. This one comes in and glances off of it, and like it's like a peel shot. They like bounce in two different directions. So these are some of the examples we're going to do. If I can go back to this slide here though, technically collisions can even happen in 3 dimensions. We don't cover 3-dimensional collisions, right? We're just either going to go straight in one line or in 2 dimensions, but we're not going to have like two things collide and then they go bouncing up in the air. Like they're either going to be in the X and Y direction, but not the Z direction. So, honestly, I think the best way of doing this is we just got to hop into some examples. So that's where most of the rest of our notes are, is a lot of math examples. So take our first one. Let's say you're playing pool. A white billiard ball moves to the right and it hits a black one. I'm going to tell you how the white one moves afterwards. Let's figure out how the black one moves. So I'm going to start by drawing a bit of a picture here so that I can draw small enough there's enough room here. Here will be my white billiard ball. I won't color it in. It is 0.15 kilograms. I'll use W for white. It is moving 8 meters per second, and it is going that way. It's going to hit the 8 ball, let's say, which was at rest. So it was not traveling. It is black, and it has the same mass of 0.15 kilograms. That's kind of our before picture. Can you guys kind of visualize what's happening here? That's the before. How much net momentum do we have before we even have the collision? Well, we really have 2 objects. This guy's providing some momentum. Actually, this guy's not providing any momentum at all, is it? It could be if it was moving, but it's not. So this guy right here, its momentum is P equals mv. Its momentum will be 0.15 times 8. So 1.2. And I'll use kilogram meters per second. That's how much momentum white ball is providing. And just to be thorough, I guess, how much momentum is the black ball providing? Well, nothing. It's stationary. Well, the law of conservation of momentum basically states that however much net momentum we have on the before, we should have the exact same net amount of momentum after our collision. Momentum is conserved, just like energy, just like mass, just like charged particles. So now I'm going to draw the after scenario. Afterwards, it says the white ball continues to move to the right, but now it's going slower. So white is now still moving this way. It's still 0.15 kilograms. It's still white, only now it's going 2.5 meters per second. But it's transferred some of its momentum through the collision to the other ball. So now the black ball, which way do you imagine the black ball's moving? Probably to the right. I can't imagine how somehow this one hits this one and then the black one goes backwards, right? So it would seem likely that if this one's still going forward, this one's probably going forward too. Again, it's got a mass of 0.15 kilograms. It's black. Our question, what is its velocity? Well, let's do the exact same thing I've been doing before. Let's keep calculating momentums. So if I go back to red here, this guy's momentum is mv, which will be 0.15 times 2.5. So what happened to the white ball? It lost some momentum, right? 0.15 times 2.5 gives you 0.375 kilogram meters per second. Momentum was lost. It used to have this much momentum. Now it only has this much momentum. Where did the lost momentum go? Transfer to the black one, right? So I mean, all I've got to do then is subtract these two, right? So if I subtract these two, 1.2 minus 3.75, 1.2 minus 1.2 minus 0.375 means the missing momentum should be 0.825 kilogram meters per second. That's how much momentum the black ball should have. And now I'm kind of like working upwards now. But that momentum was calculated by mass times velocity, and I know its mass is 0.15. So to calculate its velocity, I should just divide by the 0.15. I should be able to now reverse this calculated speed. And I got a final answer of its velocity changing by 5.5 meters per second. Yeah. Good. Okay. You're actually one step ahead of me. Because what Philip noticed here is, hang on, look at the velocities. Isn't 5.5 plus 2.5 8? Yeah, right? If you're looking just at the speeds, this guy's speed used to be 8 and 0, right? And when you're done, it's 2.5 and 5.5. Don't they equal each other? Yeah, but that only worked in this scenario because of one very specific reason. Anyone know what the very specific reason why that worked in this scenario? Yeah. No, same mass. Yeah, same mass. If the mass was not the same, it wouldn't be equivalent. Okay. For example, you're gonna have to visualize this, but when I shoot out the, well, actually I can do this. Hang on. When I shoot out this dart right here, it goes that way. You probably can't even tell, but the gun recoils in my hand a little bit, doesn't it? Right? But the amount that I'm going to notice it is different because this weighs a different amount than that one, right? If they were exactly equal, I'd expect them to both go equally in distance. Does that make sense? Like if the one going this way had the same mass as the one going this way, it'd be perfectly symmetrical. Right? But when you shoot a gun, right, the bullet's going to go really far that way, and the recoil is going to go a little bit this way because they have different masses. You know what I'm saying? So it worked in this scenario to consider mass that way, or to consider velocity that way, but it wouldn't have worked in all scenarios. I lost my board. Where did I put it? Here it is. Did that make sense otherwise? Okay, let's try another one. 2 balls of clay, a blue one with a mass of 2.3. Blue with a mass of 2.3 kilograms. And a red one with a mass of 5.6. Can you guys see how I kind of structured my notes on purpose this way? The first time I made the masses the same. This time the masses are going to be different. One of them is heavier than the other one. Red's going to have more oomph to it because it's heavier. But there's more to it than just mass. There's also speed. Blue is moving to the right at 12 meters per second. Red is moving to the left at 8.1. Don't use your calculators, but like which one has more momentum? One is heavier, but it's moving slower. One is lighter, but it's moving faster. Do you see how we have to count for both of them this time? Okay. So let's calculate their momentums.